Um, so again, welcome. My name is Brian Jackson. I'm a professor here in the physics department. For those of you who have not attended, this is the First Friday Astronomy event. This is a monthly lecture series hosted by Boise State Physics. Takes place on the first Friday of every month, 7:30 p.m. Mountain Time, all throughout the year. So even if the school is closed, we're going to still be here doing astronomy on that first Friday. These are events that have been going on for almost 10 years now. Almost 10 years. So next fall will be our 10-year anniversary. Yeah, so we hope you can join us for that um, in the fall. These events are entirely donor supported. So it's you folks that pay for us to bring speakers out to talk about space science, space policy, journalism, lots of things connected to space. These are 100% supported by you. Those donations cover the cost of bringing the speaker out, putting them up at a hotel, feeding them, all that kind of thing. And so we don't get any state money for this. We don't get any federal dollars. It's all donor supported. If you would like to help to support this, we would encourage you to purchase a calendar out in the front. We have these astrophotography calendars that our outreach students put together. They're beautiful. If you haven't seen them, they're really nice stocking stuffer, if I have to say. Let's encourage you to do that. We have another effort right now to refurbish our on-campus observatory. And if the AV can show me the campaign page, we've raised all but $10,000. We have raised $111,000 to help refurbish the on-campus observatory, and so we only have a small fraction, less than 10% left to fund this refurbishment. So if this is the kind of programming you like to see, if you want to do stargazing with us here on campus, consider donating to this program. We have information about how to donate out front. Crystal Sinclair, if you want to raise your hand, Crystal, in the back there, can provide information about how to make donations to the program. So yeah, consider getting a calendar, helping us out with the on-campus observatory. At the end of the presentation tonight, our guest speaker will venture over to that table and sign autographed copies of his book. We have a few copies of his book, but we also have flyers that he's offered to sign very kindly for you. So if you want to get like autographs and things like that, we'll get you to line up and kind of make a beeline around toward that table. Okay. So just, I want to make sure folks don't try to rush the stage after the talk. That's what I'm trying to avoid here. We also have a web form where you can submit questions, and we'll try to get through as many questions as we can at the end of the talk. But if you have a question for our guest speaker, I encourage you to visit that website. You can find the link at the bottom of that website, or you can go to that QR code and submit a question, and we'll ask those questions at the end of the talk. Our program is a big program. We have NASA funding to support a partnership with the Central Idaho Dark Sky Reserve. This is a region of our state. If you've ever been up to Stanley or out to Ketchum, you probably noticed how dark and beautiful the skies are out there. That is not an accident. There's some people out there who are very actively working to promote dark skies and help to reduce light pollution out there. And so before we get started with our main guest, I would like to invite to the stage Steve Bataille, who is the mayor of Stanley. And he's going to tell us a little bit about efforts out in the Dark Sky Reserve to educate about light pollution. Steve is currently in his 7th year as the mayor of the city of Stanley. Prior to that, he served for 10 years on the city council, during which time he was recognized by President Obama for his contributions to the designation of the Cecil D. Andrus White Clouds Wilderness and the Hemingway Boulders Wilderness. He worked for 35 years in the National Park Service, including as the Natural Resources Manager at Yosemite and as the National Wildland Fire Program Manager for all national parks. He authored the book Illustrated Flora of Yosemite National Park in 2001, and that was awarded the Henry Allen Gleason Award from the New York Botanical Garden in 2003 for outstanding publication in plant taxonomy. In 2015, he initiated the effort and worked with others to create the Central Idaho Dark Sky Reserve. And so with that, let's welcome to the stage Steve Bataille.
That working? You hear me all right? Good. technology actually works. Thank you, Brian. And good evening, everyone. I'd like to thank Dr. Jackson and BSU for inviting me to meet with you tonight to talk about something that we've been working on for 7 years now, and that is the Central Idaho Dark Sky Reserve. And let's see if I can back up one. And here it is. This is what most people come to see. That's the main attraction. And I'm just going to leave that up there for a minute just to let you contemplate that. I think it's just an image. I don't think it really needs any text boxes or talking points or headers or anything. It kind of speaks for itself. We are fortunate to still be able to see this not far from where we live, especially those who live here in Boise. But many people are not so fortunate nowadays. According to Dark Sky International, 99% of the people who live in the United States can no longer see the dark night sky from where they live. Many people today are growing up having never seen the Milky Way. I know that's true because I've met quite a few of these people, and I bet you have also. Unfortunately, it's becoming pretty common. Some of these are actually university students who have come up to help us in Stanley with light pollution research. And it's always very interesting to see their reaction when they come to Stanley and they see this for the first time in their life. Pretty amazing thing. So we're trying to preserve a remnant of what is left of the natural dark sky in the United States. A little bit of background about the reserve. It's the first international dark sky reserve in the United States. It was established back in 2017, and it covers about 1,416 square miles. So it's a pretty large area, pretty much encompasses the entire boundary of the Sawtooth Natural Recreation Area. So what is a reserve? This is the official definition of what one is. So it's a public or private land possessing an exceptional or distinguished quality of starry nights and nocturnal environment that is specifically protected for its scientific, natural, educational, cultural, heritage, and or public enjoyment. Reserves consist of a core area meeting minimum criteria for sky quality and natural darkness, and a peripheral area that supports the dark sky preservation in the core. So that's kind of a mouthful, but there's a lot of important stuff going on in that definition that tells you that the reserve is more than just about looking at the night sky. And we'll get into some of that in a little bit. Oh, my device is falling apart here. So here it is. This is what it looks like on a map. And here you can see, this is pretty much the boundary of the Sawtooth National Recreation Area with cities of Ketchum and Sun Valley to the south and Stanley to the north. And the dark core areas are right here, which were mentioned in the definition. These are basically the White Clouds Wilderness and the Sawtooth Wilderness with the Sawtooth Valley in between. So the cities and the counties have taken steps to reduce light pollution to protect this dark core area. So that sets a reserve aside from other dark sky places that you may have heard of, like dark sky communities or dark sky parks, which are basically single entity dark sky places. The reserve is a collaborative effort. It's not managed by a single entity, but by a group of land management partners, Stanley, Ketchum, Sun Valley, Blaine County, and the U.S. Forest Service, with assistance from the Idaho Dark Sky Alliance. This is what that core area looks like, looking from the White Cloud Mountains across the Sawtooth Valley into the Sawtooth Mountains. There's not a lot of light pollution coming from this area because there's not a lot of development in this area. So the important point here is the threat of light pollution is external primarily, not internal. So light pollution is the problem that we're trying to address. And light pollution is light that has detrimental impacts on the environment, and it results from inappropriate or excessive use of artificial light at night. And this illustration depicts what's happening here, that on the left-hand side, you have lights that are not shielded. So they radiate light in all directions, including up into the atmosphere, which is what obscures the stars. As you move to the right, you see that light can be shielded. The street lights, the lights can be shielded, projecting the light downward where it's wanted, a cone of light onto the surface, so it does not radiate up into the sky and impact astronomy and the view of the night sky. It's the astronomy that draws most people to the reserve. There's no question about that, and they come from all over the world to see it. But preserving the dark sky environment is about much more than just seeing stars and galaxies and planets. Light pollution has many other effects, and I'm just going to touch on a few of these very briefly here, because we spend a good bit of time thinking about these things in the reserve. Light pollution affects wildlife and ecosystems, night sky heritage, and human health. So many creatures, from migrating birds to insects to nocturnal predators like you see here, depend on the dark night environment. So light pollution affects them and can have broad-ranging effects in ecosystem. And there's a lot of research ongoing to refine our knowledge about this. Dark sky heritage is something we share with people everywhere. We have evidence of this from in our local area from indigenous people who've lived there for thousands of years and have their own stories and cultural stories about the night sky. And we also hear that from visitors from all over the world and all kinds of different cultures. So the wonder of looking up at the night sky is something that sort of binds us all together. And that's something that we need quite a bit more of nowadays, don't you think? So we're trying to help out with that. So on the health aspect of this, light trespass is one of the things that we work to reduce. Light trespass is light that is cast where it is not wanted or needed. So this can be a light from your neighbor's porch or in the yard that shines in your window at night, keeps you up at night, disrupts your circadian rhythms of light and darkness, day and night. And it's been well documented that those kind of disruptions can have major impacts on health. So there are many facets to what we're trying to do in the reserve. Light pollution starts at the local level. And so the reserve is reducing light pollution by turning off lights, shielding the lights, as we talked about earlier, or replacing bluish white lights with warmer, lower wavelength lights. And here we see a typical street light that is not shielded. The light's radiating out in every direction, including up into the atmosphere. This is a better solution. This is what our street lights look like in Stanley now. We've converted all of them to state-of-the-art shielded lights where there's a narrow cone of light that comes down, casting the light where it's needed on the streets, and no glare, no light radiating up into the atmosphere. And notice the warm amber color of the light. That's very important. The lower frequency light scatters less into the atmosphere, and it's a lot easier on the eyes. You don't have that glare at night. Local light pollution combines to produce regional and national light pollution. And here you see the extent of that in the United States. And this is why 99% of the people can no longer see the dark night sky from where they live. The reserve can control light pollution within its borders by ordinances and other laws and regulations. But over time, this threat of light pollution from urban centers continues to grow. There are still a few dark places left, like right here, which where the Dark Sky Reserve is located. Here are the lights from Boise. Notice this necklace of lights from urban areas in the Snake River Plain. This is the same view from the International Space Station. You can see the same necklace of lights. Here's Boise right here. This is becoming a major problem as the population of Idaho increases. The lights from these population centers increase. This is Salt Lake City and the Wasatch Front, and here we are looking out toward the Pacific coast of California. So, here is what we call sky glow. This is what actually comes up from the urban areas. It's this dome of light radiating up into the atmosphere. And this can be seen in many cases from hundreds of miles away. The sky glow from Boise can be seen in Stanley, which is 75 air miles away. So this is the greatest threat to the Central Idaho Dark Reserve right here. So the reserve is involved in collaborative light pollution research with the UCLA Institute of the Environment and Sustainability under Dr. Travis Longcore, with assistance from BSU. Thank you very much, BSU. And we do this by using sky cameras. And a sky camera has a hemispheric lens which can take an image of the entire dome of the night sky all the way down to the horizon, 360 degrees. And that's very useful in assessing the impact of urban light pollution, these sky glow at a distance, and tracking the trends through time. This is what one of those images looks like. So, taken from near Stanley, if you look straight up, it's very dark, but down toward the horizon, you can see the sky glow. This would be Twin Falls in this area. These are the lights of Boise, which, that's where the primary problem is right now and continues to grow. This actually is the southern end of the Milky Way with dark space on the side of it here. So that's not light pollution. And if you look on the sides, this is looking south, and you have to imagine this image wrapping around so that this is north and that's also north. And that's where Stanley is located. But that is not light pollution. That's not sky glow from Boise. That, according to Dr. Longcore, is an aurora. So that's not something we're worried about. That's something we enjoy. So in closing, here are the lights from Ketchum and Sun Valley. There's still a lot of light, but it's much better than it was a few years ago. The light pollution has been much reduced, and a lot has been accomplished and will be accomplished in the future. And I'd like to invite everyone to visit Stanley and the Sawtooth Valley and Ketchum and the Sun Valley and see the wonder of the night sky for yourselves. You can go to idahodarksky.org to learn more about what we are doing. Thank you very much.
Well, thanks very much, Steve. And just to pitch it again, we have some very lovely photos taken from the Dark Sky Reserve in our calendar that you can get out in the lobby there. Okay, well, I'm very excited, of course, to introduce our next speaker. Dr. John Mather won the 2006 Nobel Prize in Physics for his work leading the NASA's Kobe mission. He's been elected a fellow of numerous professional societies, including the American Astronomical Society, the Society for Professional and Industrial Engineers. He's a member of the National Academies of Sciences, the American Academy of Sciences, and he has numerous honorary doctorate degrees from the University of Maryland, and several other University of Notre Dame, and include in addition to other awards. But maybe the most important award, the most recent award that he won, was Best Costume for our dinner last night, where he wore his Einstein wig. It was just brilliant. So it was a fantastic costume. So I'm sure that's the most important award that you're going to hear about tonight. Okay, and with that, let's welcome to the stage Dr. John Mather.
All right. Thank you, Brian. No, we'll just use this one here. All right. Well, I'm just delighted to hear about the Dark Sky Reserve because I have not seen the dark sky for a really long time. I live in that East Coast part where it's bright light on that picture he showed us. Is my voice coming through so you can hear me? Excellent. First Fridays in astronomy, super idea. Glad to be here. I've had a wonderful visit already. I've been talking all day for 2 days with astronomy students and faculty, and it's such a thrill to be here with you. Such a degree of enthusiasm for science and astronomy especially. So today I want to tell you stories about the discoveries that we've made with the James Webb Space Telescope. Here it is on the screen. You see a gigantic golden hexagon, which is a big mirror that collects light from the stars and the galaxies and focuses it into the cameras. This is a joint international project of NASA with European and Canadian space agencies. They've all chipped in a lot. I was the head scientist over this project from 1995 when I joined to 2023, just last year. And I now have a successor. Her name is Jane Rigby. She is now the head scientist. So this is a huge project. It cost us forever and a lot of money. And I think it was all worth it. I hope you think so. So it's available to all astronomers in the world. You can work with it by sending us a proposal. And bad news is most of us will lose when we write those proposals. That's normal. But it took about 20,000 people to put this thing together that I'm showing you. So let me see if I can push the button and do the right thing. Not yet. That button. Okay, why do we do this? Well, these are questions I had on my mind when I was a small person, although I was born 23 inches long. Where do we come from? Nobody knows exactly. Obviously, our history is in some doubt. It's been discussed, and at least we had a glimmer of an idea when Darwin told us about evolution. That was one of the things that got me started into science. I read a biography of him when I was 8 years old, also a biography of Galileo about that time. So been thinking about these things a long time. What does we mean? Well, am I a bag of protoplasm, or is that something more? So that's a philosophical question, and we're not really able to tell you that one much. Are we alone? Well, in science fiction stories, of course, we're not alone. We discover planets and we go visit them. No, it was not happening, actually. Sorry. And it's pretty hard, but we do think, I think these days, astronomers usually imagine that there are neighbors out there and we should go look for them. And so far we haven't found them. I think it's pretty likely that they're far away. Anybody that is anything like us, at any rate. Is life a miracle? Well, astronomers, philosophers, physicists all tended to think that it was up until a few decades ago, because we could not possibly imagine how anything could have happened that would produce us. Now, you look at the structure of DNA or anything else and you say, how could that have ever happened? And random chance didn't seem likely to do it. But nowadays, I think we have different ideas. We think random chance could do it and might even always do it. So here's my guess, which I can't prove, that whenever we have the right conditions of chemical environment, probably warm water, the right chemicals in it, life will always start. Now, will it get to something like us? Probably not very often. It's taken the entire history of the universe for us to turn up. So are we common? No, we're probably not common. Is ordinary life common? Probably yes. That's my guess. So how far can we go? Well, no, not very far. Elon Musk says we're going to Mars, and he wants to go too. Astronomers, we can go everywhere because we have imagination. So I'm going to skip over a lot of quantum mechanical stories that I told the physics students earlier, and come back to what are we doing with the Webb telescope. So how did we get here? Well, a few philosophical things. Obviously, our world is very complex. What Stuart Kauffman in the book explains, a world beyond physics is information content. The information that it takes to describe a human being is vastly more than it takes to describe a silicon crystal. So we have to say, what are all the cells doing and how are they talking to each other? So that's way beyond ordinary information content. We can't even describe how it's done. So obviously information makes us special and different. And in particular, we can guarantee that there's not another copy of you in the universe. Even though the universe is extremely large, probably infinite, there is not another you, because you're even more unusual than that. So then how about genetics? Well, my dad told me I was made out of cells with chromosomes, and I was 6 years old at the time. Got my attention. I want to be a scientist. I want to know more about that. So I did not go into genetics. My dad was doing this because he was working on dairy cows, so we get more and better milk. So lots of other things to think about. Free will, philosophical questions. I'm not going to tell you because I don't know either. But funny, interesting things to think about. Here is a historic document from 1929. This is when a diagram was first shown to us that said, yeah, the universe is expanding. The little dots on this plot show galaxies. A galaxy being about 100 billion stars held together by gravity. On the horizontal axis, Edwin Hubble plotted the distance that he thought they were away from us. On the vertical direction, the speed of motion away from us. Oh, well, that's interesting. There's a trend plot here. Farther away they are, the faster they're going away from us. Imagine running the movie backwards in your mind. How long did it take for this to happen? Divide the distance by the speed of motion for each one, you get about 2 billion years. First time we ever had a hint that the universe even had an age you could give a number to. 1929, almost a century ago. It had been predicted by Georges Lemaitre, a physicist, also a parish priest in Belgium. And so we now call it the Hubble-Lemaitre law that says this line, this trend plot, describes the expanding universe. So, okay, the universe has an age. Now, Hubble got it wrong. Age is actually about 14 or 13.8 billion years. His distance scale was incorrect. And lots of stories there, which it took a long time to work out. Finally, we knew the better answer when we built a telescope that we named after him, the Hubble Space Telescope. Okay, so there we have it, expanding universe. So we call it the Big Bang now, but why do we call it the Big Bang? We have a very famous scientist called Sir Fred Hoyle, not the guy that wrote the rule books about games, but a brilliant scientist. He called this thing the Big Bang because he thought it was stupid. And he just didn't like this whole idea. And the upshot is we are all confused because when you call it a Big Bang, you think of a firecracker. How can you help thinking of a firecracker? But this exact opposite of what astronomers have seen. Firecracker is an explosion at a particular place in a pre-existing space and time. That's not what we see. We see the expanding universe. Everything's running away from us. We imagine the entire infinite universe is running away from itself, into itself. So this is quite the opposite. So thank you, Sir Fred, for fooling us all and confusing us all. So no, the universe was never a point, and it's a lot of things the popular press has told you were just wrong. Sorry. Anyway, here is the beginning of our understanding of the expansion. So what do you do next? Well, a couple of things. In 1948, we had some nuclear physics we knew. And so we said, okay, we'll calculate what would happen if this was the universe that we have. And you could predict that it should have 75% hydrogen and 25% helium from the properties of neutrons, which it does. Okay. So then can you tell us something more? Well, you can tell about how hot it was at the time. So two guys, Alfred and Herman in George Washington University in Washington, D.C., they said it should have a temperature of about 5 degrees Kelvin now, and would have been trillions and trillions of degrees when the universe was young. So go measure it. No, nobody did. 1965, somebody measured it by accident. They were building radio astronomy tools to look at the Telstar satellite. And there's a little extra noise in the radio receivers. It turned out to be the cosmos, the Big Bang itself. So how bright is that? Well, it's not very bright, but some of you remember we had TVs with antennas that you put on the roof. And if you tuned in the channel in between channels, you would see snow. Not real snow, but snow on the TV. About 1% of those little speckles comes from the cosmos. So it's not that hard to measure now that you know it's there. I even have a young friend who did his high school science project measuring that with the TV equipment. Oh, so there's a lot you can do now that you couldn't do then. 1948, we didn't look. 1965, we did look by accident. Those guys got the Nobel Prize for discovering that heat. 1970, I'm a graduate student in Berkeley. I think, what am I going to do for a thesis project? My thesis advisor said, we're going to go measure the cosmic background radiation. Anything we find out will be new. So, okay, he designed an apparatus. The students helped build it. We launched it. It didn't work. I got my thesis about a project that didn't work and said, I'm lucky to get out of here. And I had a job lined up in New York to work for NASA. Well, okay, 6 months after that, NASA said, we want proposals for new satellite missions. I said, boss, my thesis project failed. We should try it in outer space. We'll get real engineers to make it go. We wrote a proposal and it was eventually accepted. So here it is, as we imagine it to be in outer space. It's called the Cosmic Background Explorer satellite to measure that cosmic heat. And this is the one that earned a Nobel Prize for us. It was much harder than we thought it would be, but it was the first of its kind. It had 3 instruments on board, 2 of them to measure that cosmic heat. And one of them was to measure the spectrum. Is it the right color? As it should be coming from the Big Bang? And is it the same brightness in every direction? And nobody had ever known a measurement of that. So practically the first time to try it. So we discovered that it had hot and cold spots in it. And here's a map of the hot and cold spots. So the early universe was opaque because it was hot and dense. The current day universe is almost empty and very transparent. So we're able to look back in time by looking out far in space to see how far back can you look to where the universe was actually opaque. This is the universe as it was about 400,000 years old. And we've made a map of the entire sky and plotted as an oval. So the pink and blue blobs are telling us that it's not exactly the same everywhere in the original material. The contrast is very small, apart in 100,000 variation from place to place. So Stephen Hawking saw that picture and he said, that's the most important scientific discovery of the century, if not of all time. Okay, thank you, Steve. So I was just proud that we'd been able to measure it at all. So why is it so important for scientists? Number one, we wouldn't be here without those spots. Something had to stop the expansion of the matter and pull it back. Gravity had to pull us back in so that we could have stars and galaxies. We wouldn't be here if something hadn't broken the symmetry. If the universe was completely uniform, gravity could pull, but it wouldn't know where to pull. It would keep on expanding. It would be uniform forever. So spots are here. That tells us the initial conditions of the universe. If you can understand this, you should know how galaxies would grow. Number two, most of the spots come from cosmic dark matter, which we now believe in. We cannot see it. It's transparent, but we're pretty sure it's out there. Number three, there's cosmic dark energy that's making the universe expand faster and faster all the time. And so the evidence of that is in these spots. We've measured it much, much, much better now. And so we now have what we call a standard model of cosmology. I think we understand the whole darn thing, except, of course, dark matter and dark energy, which are complete mysteries. So we know they're there. We don't know much about them. Nobody asked for them. Nobody predicted them. Nobody said they should be there. And so it's one of the top topics in physics these days is to go look for that. And we don't know if we'll ever win. It might be totally transparent. It'll never do, it just may never show up in a laboratory. Nevertheless, it's fun to work on. So here is me showing my spectrum. That curve is a measurement of whether the cosmos has the right color to be left over, that radiation is left over from the Big Bang or not. So the curve has error bars, which we didn't know yet, but in the end, there are 50 parts per million. So it's an extremely good measurement. And we were very proud of ourselves. It meant that the Big Bang is the right story, that we should call it the expanding universe story. And these days, by the way, you could measure it about 1,000 times better than that. Now, does anybody want us to measure that? Well, yes, but not enough to pay for us to do it. So, but technology has advanced tremendously. There I am with the King of Sweden receiving my diploma. And later on, I got a check and a medal, and it was really lovely. And parties and speeches for 10 days. They know how to celebrate. Got to have dinner with the Queen of Sweden. So anyway, what else do we do? Well, shortly after the Cosmic Background Explorer was launched in 1989, the Hubble was launched in 1990, and we put it up there, and darn if it didn't work either. It was not in focus. We had made a mistake in testing the mirror. And it took us a while to figure out what had gone wrong and what to do about it. So a few years later, astronauts went up and they put in new equipment and we got sharp pictures. And it was brilliant. And the internet was new. So when we published our pictures, the internet crashed. Could not keep up with the demand for our pictures. Anyway, soon after that, we said, now we know what we need to do next. The Hubble telescope showed us, as far as we could see out into space, the most distant galaxies we could see. They're not very different from the ones we've got today. We hoped we would be able to see the first galaxies growing with the Hubble telescope, and we could not see far enough back in time. So please build us another more powerful telescope that can do that. And by the way, also please start learning how to look for planets around other stars, because that was just the one when the first planets were measured orbiting around other stars. Okay, so a whole new subject just opened up. Too hard to do, but better figure out how to do it. So they wrote a book, and the book said, please build a new telescope. And so that's when I got called in. Would you like to join this new telescope project? The coolest thing that I could possibly imagine doing, building the world's most powerful telescope. So engineers had already been thinking about how to do this. Scientists already been thinking about why we should do it. And so we built it. There it is, orbiting in outer space, at least according to our imaginary picture. It tells you on the chart that Europe and Canada and the United States worked together to build it. We hired a big company, aerospace company called Northrop Grumman, to do the spacecraft portion. The instruments came from around the world, from Arizona, from Canada, from Europe. Operations is done by the Space Telescope Science Institute in Baltimore. That's the same place that runs the Hubble. And by the way, the same place that releases the data to you, so you can fetch the data from our computers. The telescope is about 6.5 meters in diameter. It's a hexagon, and it is cold. It's cooled down to about 40 degrees Kelvin, 40 degrees above absolute zero, so that it does not emit infrared light. There it is. We said when we started, we will guarantee 5 years of mission life. Well, we are going to do a lot better. Here is the launch. It was launched from French Guiana on the north coast of South America on Christmas morning, 2021. So why do we go there? Well, number one, the Europeans are buying the rocket. So, and French Guiana is part of France. So that's where they have their launch facility. Why did they put it there? Because you can launch eastward, and it's near the equator. You get the maximum benefit of the spin of the Earth. So good reasons to go there. It took a little bit of negotiating to get that idea approved, but anyway, the launch was perfect. And it was so perfect that we didn't have to spend any fuel adjusting the orbit on the way up. That's why we're now hoping for at least 20 years of flight. So we'll be busy doing what we do, but hope for a really long life. I'll show you where we put it. We put it orbiting around what's called the Lagrange point 2, which was found in 1750 by Leonhard Euler. So typical case where we name something after somebody else. But Lagrange did find the other two. These are places where if you put an object there and give it the right speed, it will stay orbiting around the sun once a year and maintain this pattern. So we choose this one because if you're standing there at L2, you put up your umbrella, you're always in the shade. The Earth, sun, and the moon do not shine through the umbrella. You don't actually go all the way to that point because it's in the shadow of the Earth. You orbit around it. Plenty of space out there. No collisions with other missions are expected. Anyway, that's the place we put it. And then we say, well, I've got to unfold this thing. This telescope is much bigger than the rocket. I have my scary movie to show you. Here it comes. Telescope unfolding by remote control command. And it took this thing that I'm showing you actually took 2 weeks. Pop out the solar panels, make sure you got electricity, the antenna so you can talk back and forth to Earth. Now we're unfolding the structure that holds the umbrella up, the sunshade. And this marvelous drawing is done by computers, of course. This is one of those technology advantages that we didn't have when I started at NASA. We used to draw telescopes with pencils. And that worked, but it was a lot harder. Here we're unrolling protective covers. We will shortly stretch out the sunshade. We do this by pulling on cables and pushing on things. By the way, how do you make something like this work? You complain, you worry, you get committees to review your work, and you make 2 ways of doing everything that might matter, and you test. We tested the unfolding of that shade 4 times before we were sure that it would work. And so there it is. It's in the image. It's now fully unfolded, but it is not ready for work. It's still warm. The telescope will be cold. It took us altogether 6 months to get it cooled down and focused and ready to go. So 6 months after launch, and then it took us just a few more weeks to have a picture ready for the president to distribute. We'll show you that. So why do we observe infrared light? Well, 3 reasons. Here's number 1. You can see through dust clouds. Space is full of dust. Where does the dust come from? Stars that blew up and exploded. Stars burn hydrogen and helium and turn them into heavier elements. When they're old and they run out of fuel, they blow up or do something. So the dust goes back out into space. Everything you see in this house was made from exploded stars. Your exploded stars, the calcium, the iron, the steel, everything came from stars that blew up. And so what we're looking at here is a cloud of material that's been enriched by stellar debris. And there's a star in the middle of it you can barely make out, which is sending out jets of material, and you can hardly see them. If you use an infrared picture, you can see it a lot better. And you can see how much more transparent that dust is at the longer wavelengths. So we knew this is a way to see inside dust clouds. And why do you want to see inside? Because that's where stars are being born today. Stars like the sun with planets like the Earth being born now. So please build a telescope to see in. Number two, some things are not warm enough to send out their own visible light, but it is important. If you were out in space, you're emitting about 500 watts of infrared power, and we'd be able to see you at an immense distance. We could see a bumblebee at the distance of the moon, so we could see you halfway across the solar system. Anyway, so to see something that's not warm enough to emit visible light, use infrared light. So here's a picture of a star that's in the process of blowing up. It's shedding dust grains, and they're emitting light. So part of the story again. Third reason is, of course, the universe seems to be expanding. Galaxies are going away from us. We need to be able to pick up the light that has been stretched to longer wavelengths as it's coming to us from far away. So this is just a sketch of that idea. Right there, where there's something sort of controversial in the title, we say space expands. You can't tell what space is. Space isn't a thing like a crystal, but the distances between things are increasing. And so we say space is expanding. We could also say, well, stuff is running away. So we're just trying to clarify the ambiguity of the term. So anyway, what did we see? This is our first data release from July of 2 years ago. We took a picture with our near-infrared camera, and it shows basically three things on this picture. Number one, there are stars with the 6 spikes sticking out, and they're 6 because of the diffraction of light. Our mirrors are hexagons, so when light comes to a straight line like that, it can sort of scatter and bend sideways. So that's why the spikes are coming out. But the stars are not very interesting to us usually, because we got a lot of them already. In the middle is a truly gigantic, massive galaxy, and several others with it. And we choose this one because it has so much gravity that it can bend light. So these are called gravitational lenses. Einstein told us this could happen. He never guessed we would ever be able to see one, or that certainly would never guess that this would be how we would use it. It's another lens on the telescope. Now, it's not a lens you would have designed, because it's sort of random. It's produced by where are the galaxies and how much mass do they have? But nevertheless, we can use this because some places have a lot of magnification. So see those funny looking pink arcs? Those are distant galaxies, and sometimes you see 2 or 3 or 4 or 5 arcs that all are multiple images of the same very distant galaxy. So we get magnification of 10 or 20 or even more sometimes. So a hugely powerful tool to look for those most distant early galaxies. So we've been doing a lot of this. I'll show you some more pictures of this. So the early galaxies that we wanted to understand are not like what we thought. The story of the expanding universe is not in trouble, but our understanding of how galaxies would grow from the primordial material was probably all wrong. And so we're looking at trying to understand this fact. Galaxies grew very quickly, and some of them are too big and too bright. And a few of them are round, but most of them are not, because galaxies don't form round. They form as little stringy things. Typical, mostly of they're stringy. So they're just not round yet. They will eventually be round, but only after they spin around a few times. So should we have understood this, expected this? Well, maybe, but we didn't. Here's one illustration that even in the space between the galaxies, they are stretched out along threads and strings in space. So probably just the result of gravity working on what was there before, but we were able to work out the distances of things and say in 3 dimensions, how are they arranged? So long stringy thing in space. So we've even been able to magnify a distant galaxy and see that it has small clumps in it. These are called globular clusters. If you're an amateur astronomer, you know where some of these are in our own galaxy. You can go see them with binoculars and they're beautiful. So this very distant galaxy has a couple of dozen of them that we can see because of the magnification of the gravitational lens that Einstein told us about. So we're beginning to learn about this question: which came first? The galaxy? Did it form galaxy and then form clusters, or did the clusters form first and then merge together to form a galaxy? Don't know yet. Similar question, every galaxy has a black hole now in the middle. But we don't know whether that was the nucleus for the galaxy to grow because the black hole was there first, or did the galaxy produce the black hole? So ask again in a few years. We may have a better story for you about that one. Here's an example where the magnification curve is shown to you. On the right-hand side, there's a little red curve that shows where the magnification is almost infinite. In other words, 10,000 times or more. And wow, once in a while, in fact, quite often, there's a single star that lands on that spot, and that single star at immense distances can be observed. And we say, is it like the stars today? More or less. So beautiful, beautiful pictures and startling surprises in what you can see with them. Here is one of the most remarkable recent discoveries. People just were looking at our pictures and they said, look at that. This funny stretched arc is actually a triple image of a single galaxy. And this is unusually for us. This is a galaxy that has a supernova going off. Supernova is a star that blows up, almost completely destroys itself. And for a few weeks, it is 10 billion times brighter than an ordinary star, as bright as a whole galaxy. So there it is, happening in this distant galaxy, and we can work out the shapes and the history and many things that are important to astronomers. So it's not only beautiful, but important. So there's another, this is a most beautiful picture. This is taken by the Hubble telescope. The big fat galaxy in the middle has magnified images of other galaxies, and there are some of them in here which have 4 or 5 copies of the image of a distant galaxy. So thank you, Einstein. You told us it would be there, but we didn't know we'd ever use it. So here is a picture of the most distant object that we have yet discovered. That little red ear on that image on the upper right is the most distant object. It comes from the time when the universe was 290 million years old, which is a very small fraction of the total age of 13.8 billion. And it comes from the time when the universe was very compressed. We call it this is labeled with what we call the redshift. It means the distance between galaxies at that time was 15 times smaller than it is now. So very, very distant. We're learning to answer the questions that drove us to build that great telescope. Now, how do you find these things? Well, look, there are thousands of little dots on this picture. Now, which one is the interesting one? So you have to go look and see about the colors of the little fuzzy dots, and some have them unusual colors. And you say, well, that maybe is a good candidate. I better go look at it better. So you open up the spectrometer and say, show me the spectrum of that object. So a spectrum basically spreads out the light of the star or galaxy into its colors. And the most distant galaxies will have a very characteristic shape of that curve. So that's how we found that one. Look at a lot of little dots and hope for the best. So this is mine showing to you because it's an example of what happens when galaxies collide. There are 4 galaxies that are about to join together. The one is on the right. The one on the left is a lot closer, so it looks different. It's more speckly. We can see that the 2 in the middle are in the process of colliding and producing debris that's popping out. Those orangey pink curves are where new stars are being born today. Here is our Cartwheel galaxy. We knew about this one before the Webb was launched, but now we have a new and more informative picture. What we see is the result of a collision. A galaxy went right through the middle of the big galaxy, and what we're seeing is a splash ring that came out from that collision. So gas was expelled from the center of the big galaxy. It was excited, compressed, and turned and made able to form a new generation of stars. So that whole ring of bright things there, these are stars that all have the same age, coming some number of millions of years after the collision where the other galaxy went through the middle. Here's a picture showing an ordinary galaxy, but now seen with infrared light. This galaxy has holes in it. So why would a galaxy have holes in it? Well, the stars do not actually show that the galaxy has holes, but the gaseous material in the dust shows holes. So that's because there is same as a sponge. A kitchen sponge has holes because of gas pressure. So these holes come because a previous generation of stars was so bright and liberated so much heat and energy, it pushed the gaseous material away. So a kind of eruption in the middle of each hole, and you see that there are many holes in this galaxy. This is a picture we call the Pillars of Creation. This is a place we knew about already, of course, but we had to look over here. This is a place representing star formation today. So you can see from the way the picture looks that there's a wind blowing through the picture from the top right to the lower left. The wind is blowing around this cold cloud of dust. And now I should say, why do we care about cold clouds of dust? For a new star to be born out of the gaseous material that's out there, there has to be something that has enough gravity to overcome the pressure of the gas. So colder is better. If the gas will be cold, then the gravity can pull against it and pull it in to make a star. Places where stars are being born inside the dust clouds. And that's again why we needed to have the infrared telescope to see. See through the dust clouds and see inside and see the light. So you can even see a few places in this picture where stars are being born right at the tips of these clouds of dust. So eventually we'll be able to tell you a lot more about how this happens. Right now, we're still in the process of appreciating and understanding the data. This is a picture showing that galaxies have winds coming out. Why is a wind going to come out of a galaxy? Those holes that come from the hot gas, sometimes whole fountains of material will be expelled from a galaxy. In this case, they're called polycyclic aromatic hydrocarbons, which is to say, as chemists would call it, soot, coming out from a galaxy because so much chemistry is going on. And so much energy is being released. We've even seen buckyballs in space. Buckyballs are little molecules of carbon that have 60 atoms arranged sort of like a solid soccer ball, but bigger. Those are called buckyballs because Buckminster Fuller talked about those things. So we've seen them in space. Here is something we saw with the Webb telescope in 1987. A star in the southern hemisphere blew up, and you could see it from the ground with your own eye. It's called a supernova, and it's the first one we've been able to see here locally since 1604. So we felt very fortunate. Everybody looked at it, and just with a Webb telescope, we were able to see there's a sign of a neutron star, which is the debris, the remnant of the original star still left in the middle. So first time we'd ever been able to track that down. This is a picture not from the Webb, but from the Hubble telescope. We've found a place where there's a black hole in the middle and you cannot see it. See the little black circle in the middle? Nothing's there that you can see, but we have seen the stars nearby orbiting around it. And we've been watching this spot for 20 years. And the stars move fast enough and you can calculate their orbits and say, I think there's a huge object in there with about 1,000 times the mass of the sun. But it has no light, nothing's falling into it, nothing's getting compressed. So this is part of the mystery of where do the black holes come from and how do they grow? So it's in there, we don't know how it got there. This is a new star that's just been born. It's in the process of being born. And what we see here is that we cannot see the star. It's hidden in the middle in that black dust cloud. And this is quite typical. A young star will very often have jets of material squirting out from the north and south poles. Now, the infalling material in the orbiting dust cloud kind of forms nozzles. And we don't quite know how this works, but you can see huge amount of energy is coming out in those jets. Here's one that's much closer up. Here's the closer image. You can see the orbiting dust right in the middle of the hamburger, in the middle of the bun. There's a star, and we will come back to that in 100,000 years, and you'll see that the dust is gone, and there will be planets in there. Most stars have about a dozen planets, 5 or 10. There are a similar number of planets have been expelled. So there are a lot of stars, a lot of loose planets. We call them rogue planets running around in between the stars. Anyway, so we're now observing the process, trying to understand it. We have found some surprising things. We have found planets that have no star. These are objects the size and mass of Jupiter, and they come in pairs in the Orion Nebula. Now you can see the Orion Nebula with your own binoculars and see that it's got some stars in it. It took this equipment to discover that there are pairs of Jupiters out there, and there are several dozen of them, and it was a huge surprise for astronomers. Of course, we thought planets are formed around stars because they do so in the solar system. We did not know they could form all by themselves. So we've been looking at planets around other stars, exoplanets, and this is our most powerful technique. We've got a catalog of about 6,000 stars where this happens, or 6,000 planets, I should say, where a planet goes in front of a star and blocks the starlight for a while. Okay, so now you can tell there's a planet there. You can tell how big it is, calculate how warm it is. And now you say, well, does it have an atmosphere? If it does, some of the starlight going through the atmosphere will, on our way to our telescope, will be absorbed by that atmosphere. Does it have clouds? Does it have the molecules? And the answer is yes, we can do this. So far, we do not have any sign that there are Earth-like ones like this, but the big ones we can analyze. So I'll show you a few examples of what we've seen in them. Here's a big fat planet quite close into its star. It is hot. It has 2 chemical elements, sodium, potassium, as well as 4 different molecules you can recognize. So how do you recognize a molecule? The molecules can absorb wavelengths, some wavelengths, and not absorb other wavelengths. So we spread out the starlight into a spectrum. We say, how much does it change when the planet goes in front of the star? And the difference tells us what was in the atmosphere of that planet. So this is the calculation we're showing you. In this case, it says, I think about 2% of the starlight was intercepted by the planet. So it's a pretty large planet. But you can see it's a very fluffy planet because at some wavelengths, it seems to be much larger. So that's one. Here's another surprise we got recently. There's a star called Beta Pictoris. It's the second brightest star in the constellation of Pictor, which I think means painter. Anybody know their Latin? Anyway, we saw that it changed. When it was first observed 20 years ago, it had a particular spectrum, and we interpreted as that a couple of asteroids had crashed into each other. And now we look, and again, it's not there anymore. The dust has gone away. This is a planet that seems to have a combination of hydrogen and an ocean. It's a hot planet. They've invented a name called Hycean, sort of hybrid of hydrogen and ocean. It's got a lot of different molecules in it, including this rather odd one, a claim that it's got dimethyl sulfide in it. You might remember a year or so ago, there was a public claim that this was a sign of life. Well, no, not really. That's a weird place to think that it could be alive. But it's an interesting molecule, and we have to figure about that. Here is one that has sand in the atmosphere. It's really hot. So sand grains, because actually quartz crystals in the atmosphere of another planet, because it absorbs a lot at a wavelength of about 8.5 or 9 microns wavelength. Here is one we actually saw a direct image of the planet. In the middle of the picture where the yellow 5-pointed star is, that's where the star itself is. And off in the upper left corner is an image of the planet. This is one whopper of a planet, and it's very bright, but there it is. Looking at the solar system, we've got beautiful pictures of our own solar system. Here's good old Jupiter. The red dot is not red because we're looking at infrared wavelengths. We have to make up our own colors to show you something. And Jupiter has an aurora on north and south sides because it has very, very active magnetic dynamo. So when we get an aurora here, it's rare that we can see it from here. On Jupiter, this is a constant thing. It's always being bombarded that. Now, all of the giant planets have rings. There they are. We've recently gotten a lovely surprise that many of the planets have satellites with interesting features on them. Ganymede is a satellite of Jupiter that was discovered by Galileo. It's fairly cool, but we have seen hydrogen peroxide on the surface of a satellite of another planet. Look at that. Again, it's done by looking at particular wavelengths. We know what wavelengths hydrogen peroxide emits or absorbs. We found carbon dioxide orbiting close above that same satellite. Again, by looking at particular wavelengths where the carbon dioxide emits or absorbs. Sulfur dioxide, Io. Io is the closest large satellite of Jupiter. It is so hot, it's got sulfur volcanoes. So the sharp picture we have here is because we went and visited years and years ago and took up close-up pictures with cameras on the way out of the solar system. Now we've got pictures we can do from here, and here this is with the Webb telescope. We have, or I should say, in this case, Europeans have sent a probe out to look at the moons of Jupiter. They're all interesting. So except for Io, the four bright ones, so Europa, Ganymede, and Callisto are all called icy moons. They all probably have ice over the surface of a liquid ocean underneath. Europe has sent out this probe last year, and we have been looking at Europa a lot because we know from previous observations that it has water eruptions. Europa is, again, we know it's got an ocean covered with ice. There are cracks in the ice blocks, water comes spitting out. When we first knew that there was an ocean, we said, oh, we're going to have to build a submarine with a nuclear reactor to melt our way in. And we don't, because we can wait for the water to come out. So we have designed this apparatus, this thing called the Europa Clipper, which is on its way to Jupiter to look at Europa. I'm going to get close up and see if there are organic molecules in the water jets that are coming out between the ice blocks. So why do we care? Well, is that satellite alive? If they're big, fat organic molecules and they're more than just simple ones, you could say, yeah, something's really interesting going on in that ocean. So we had to wait because October 10th was the day of a hurricane going through Florida. So we had to wait for the next week. We have attacked an asteroid, the first time we ever did that. We got to watch it with the Webb telescope and the Hubble. So you can see the debris flying out from the collision. The 6 spikes sticking out of the image of this object are a diffraction of light, but the rest of the stuff is real debris coming out. So we've seen what happens when you drop a block of metal onto another asteroid. So we're learning how to protect you from killer asteroids. Congress gave NASA the job of finding them all. And, well, we can find the big ones. We cannot guarantee to find the little ones. There was one that hit in Chelyabinsk in Russia just a few years back, and we never would have found that in advance, but it only killed a few people. By the way, it killed people because they ran up to the window to look. And then when the sound wave, the shock wave, arrived on the ground, the windows shattered and the people were killed by the glass. So do not run to look out the window when they're getting hit by an asteroid. We are sending a probe to Titan, and we're looking at the Titan with the Webb telescope. Titan is the only satellite that has a big, thick atmosphere. It's enough to support a helicopter. The picture of the quadcopter in the upper right corner that will be landing there in 2034. And so there's a huge engineering miracle behind that one, which I could tell you later. But why are we going to do this? Because Titan has a fascinating structure as well. The surface has liquid rain, lakes, rivers, clouds, and it's a fascinating place to think about. That's ethane and methane. So, well, could that be alive? Nature has done the experiment. If you could make a new form of life that used ethane and methane as solvents instead of water, this is the place you would look. Do you think it's there? I doubt it, but we certainly ought to look. And then underneath, there's a much more interesting structure, which we probably may or may not ever know about. But we have an idea that this is the structure of Titan, with numerous shells of different material. And maybe there's some sign of the liquid ocean of water underneath all of that. I don't know if we'll ever know, but there it is, something to think about. So here's a satellite picture. I'm just showing you because it's beautiful. People are busy interpreting the meanings of all these things, but notice the names of the satellites of Uranus are Shakespearean. Most of the others are Latin or Greek. Anyway, also, by the way, this is the one planet where the spin axis is more or less in the plane of the orbit. So this is why we get to look down on the top or the bottom, according to your perspective. So there it is. This is gets to the end of the story about what we're doing with Webb, and here is something to look forward to. In about 4.5 billion years ago, the Andromeda Nebula will be arriving, and we will have a wonderful collision to look at. So a dark sky night will be a different kind of dark sky night. Now, this is only the Photoshop version. This is not the real thing, which will be much more complicated. Will we be here in 4.5 billion years? Well, the sun will still be here. In about 5 billion, it will become as large as the orbit of the Earth. And that'll be a hard time to be alive. After actually about 1 billion years in the future, the sun will be too hot for us to live here. But anyway, that's the short version of the future. And let me see how much time we have before we have questions. So what is it, time to stop and have questions, or should we go on a little bit?
You've got time.
Okay, I have a few more things I wanted to show you, which is what are we going to do next? So, of course, you can find everything on the internet now. But what are we doing next in space astronomy? Europe launched this mission about a year ago to look for dark matter and dark energy. It's a small telescope, but it's working fine. So they're going to be looking at millions and millions of galaxies to understand the effect of dark matter and dark energy on galaxies. We are finishing up this telescope in South America. It's called the Vera Rubin Observatory. She was the woman who was most important in discovering the effects of dark matter on galaxies. So anyway, this telescope is enormous. It's 8.4 meters across the mirror. It has 3 gigapixel camera. There are so many bits coming in that we have to count on Moore's law to help us get the computer to deal with it. We are expecting 10 million things to change every night compared to last time we looked. So every 3 nights we see the entire sky that you can see from that spot. And well, lots and lots of bits. We'll need computer intelligence to find the patterns, to find all these things, and to tell us when we have to follow up something because it's really special and different. There will be asteroids and comets and all kinds of things coming through in this camera. And as you probably heard, there will be streaks across the sky because the Starlink satellites and the other ones that are being put up by other companies will be going across also. So we're not getting them to go home, so we're going to have to figure out how to deal with that. But at any rate, we will have a huge amount of information and lots of fun with that. Then NASA is going to be launching this one, the Nancy Grace Roman Space Telescope, in 3 years. And it will be also looking again for dark matter and dark energy, but in addition, looking for planets. We have an instrument on board to block the starlight and look for the planets around the star. It's called a coronagraph. And we do not expect to be able to find an Earth orbiting a star like the sun, but we'll do everything we can to find out what you can do. And maybe we'll get lucky and find something really surprising. So that's coming in 3 years. And Then in about 15, 20 or something years, we hope to fly this one. The Habitable Worlds Observer would be as large as the Webb and would be designed so that you could image an Earth orbiting another star like the sun and get a spectrum and say, does it have oxygen and photosynthesis? So that's in our future, and it's, quote, only 20 years maybe away, depending on how good we are at our job and how generous the Congress is. But I think this will be a very exciting project, and it's astronomers have basically said, yes, that's what we all want to have next. So wish us luck. It could happen. And with any kind of luck, we'll still be here to find out what they say. So the end and the beginning. Thank you very much. Okay, so we have questions coming in.
Yes, I have several questions.
Okay.
Yeah, so we have a lot of questions. We'll start with the one I asked you earlier. Do you have anything named after you?
Ah, yes, an asteroid. I have a friend who discovered an asteroid, and the people are entitled to name them after their friends.
What kind of asteroid is it? Do you know? What type of asteroid do you know?
Only all I know is it's very small.
Yeah. How can the James Webb Space Telescope use transit spectrophotometry to detect life on other planets or even photograph its surface? Can we use spectrophotometry from James Webb to detect life on other worlds?
Ah, well, we wish we could. We don't think we're going to be able. So a really strong sign would be oxygen, but we don't think we can pick it up. We'd not cover the white wavelength range. So probably not.
If you had no budget limit, what project would you start?
I would start that one I just showed you, the Habitable Worlds Observatory. It's a multi-billion-dollar project. So anybody got a deep pocket over here?
Yeah. We have some very generous donors in the audience.
Yes.
We know that.
Well, that'll help. That'll get us started.
Let's see. Are there any? You answered that question. How about how have your work and discoveries impacted your philosophy towards life and existence?
I wish I had a philosophy of life and existence. I'd say it's not my work that's influenced that, but sort of interacting with other people. A year ago, I married my sweetheart, my neighbor. We both had lost our spouses, and now we go to church. And I didn't do that before. So every week I'm thinking about the meaning of life, sin, forgiveness, cooperation, trying to understand what might be expected of us and what we would like to accomplish. So that gives us a different feeling. It's not an abstract question when you're with people.
Let's see. There's a question about were origami experts involved in designing the folding mechanisms for James Webb? And if so,
yeah.
Yeah.
I don't know if we were expert, but we had a catalog of 50 different ways to fold that thing up. And we chose one, of course, because a particular company thought that was the best answer after serious thought. But the other company that competed with them had a whole different answer.
What sparked your interest in cosmology?
It's sort of random. I'll tell you, I was thinking about what to do for my thesis project in Berkeley, and I was going around to talk to people. What should I do? I want to be a theoretical physicist like Richard Feynman. He's cool. Are you wealthy? No, then don't do that. So talk to faculty who's got something to do that a graduate student can start with. Well, they're going to go measure the cosmic background radiation that had only just been discovered. Well, that's cool. I'll do that. So that's how deep my thought was.
Is AI being used to interpret images from James Webb?
I'm not sure how much is being used, but certainly people are trying it. We don't quite know how much to trust AI. yet, but we certainly are using what we call machine learning. We show the hardware, the software, a pattern or a bunch of patterns. They find more of these, or find me something that I don't know about, something that's unusual. So there's a lot of work on this. And there's also something that we're doing that isn't specifically about the Webb, but we have these giant computer simulations. I can get a movie of how the galaxies grew from a computer. It's very expensive to do it. And the hard problem is connecting the very large scale universe with the tiny scale things that happen in a galaxy. So you can't do it properly with a computer, but you can say, okay, machine, I've simulated the small scale stuff. I simulated one galaxy. Now show me how to stitch that together with the large scale stuff. And so we've cut the cost of computation by about 100. So huge impact already in understanding the pattern of the galaxies.
Do you think, let's see, do you think time has always existed in the universe?
That's a tricky question, isn't it? Because to exist is to exist in time, isn't it? So the logic of it's a little odd, but my take on it is there's not such a thing as a time before time. It doesn't make any, we don't know what that word could possibly mean. So in particular, there's not a first moment in the universe. Time equals 0 is not included in the set. Suppose I say, well, I've got a circle and I can either include the edge and the center point, or I can exclude them. How about a circle where I don't include the center point? That's what I think the universe is more like. Don't include time equals 0. You can get as close as you want to time equals 0, but you can't actually get there. That's how I think it is. Mathematicians call it this difference between a compact set and a non-compact set. So they've been working on this for centuries. We're just coming to try to understand what is the physics about it. Honestly, we don't know. What was there before the Big Bang? There are lots of ideas. A lot of people will tell you it was a bounce, that there was something before and the universe collapsed in and then bounced and came out again. I don't know. We may never know, but at least it's not ridiculous. It's not ridiculous to think about it. So people do.
What are your thoughts on the observer effect and why do they happen? So will we ever find out why? Is it related to Schrodinger's cat?
Oh,
yeah, I think that's the
the
question.
observer question. So people talk about quantum mechanics, and this is jumping to a whole other subject, as though when you observe something, you change it. So I think a better model is it has nothing to do with us or consciousness or anything. We've got a quantum mechanical system that we're thinking about, and we've got another quantum mechanical system that we're built to observe it with, and the two of them interact and they do something quantum mechanical. And that's not an observer effect, it's quantum mechanics just running along as it does. So the way I picture it is, we describe the universe with wave functions in Schrodinger's equations, and we say, okay, it just runs by itself. But when we try to understand what is it doing, then we have to imagine trying to measure a wave. How do you measure an ocean wave? Well, you say, well, it's this high over here at this moment of time. That doesn't mean you measure the whole wave. It only measures a little tiny bit of information about the wave. So it's like that with quantum mechanics. You measure a little bit of information about it, but it's not the whole thing. And you can't measure a wave without disturbing it. So that's part of this, what we call observer problem. But it's got nothing to do with us.
What advice do you have for students planning to study astrophysics?
Short answer is do it. I think it's one of the most exciting subjects we have in science these days, because we have so many kinds of new information coming in and so many new tools to play with and work with to make progress rapidly. So it's a very exciting time to be an astronomer, to do astronomy. And of course, you're not all going to replace your professors. So after you do astronomy as much as you want, go do something else. One of my young friends graduated from Yale with a bachelor's in physics and astronomy, and she works for NVIDIA selling supercomputers to people like us that want supercomputers. So there are a lot of paths that you can take following up on your curiosity and your interest in the physical world, and then go do something with it. but hardly ever an unemployed physicist. We're just doing something else.
What is at the center of a galaxy?
At the center of a galaxy, well, sometimes nothing but stars, but most usually there's a black hole in the middle. And this is the big question people ask. Well, how did that happen? How do you know if there's a black hole in the middle? Well, sometimes it lights up because stuff is falling in and gets compressed and heated to a great temperature. So we have the one in the middle of our own galaxy. And we even know how massive it is because we can watch stars orbiting around it and calculate. So we've got one. Other galaxies have them. Usually they have a few percent of the mass of the whole galaxy is in the black hole. Once in a while, it's the opposite. There's some black holes that seem to have no galaxy left. And so some great mysteries are turning up lately.
Does the universe expand faster than the speed of light?
It depends on what you mean. Yes, distant parts of the universe are rushing away so fast from us that we can't ever see them again. And so faster, Einstein said nothing can go faster than the speed of light, but that means locally. I cannot go past you at a greater than more than the speed of light. But if I'm way over there, I'm going away from you, I can go faster than the speed of light because we're not in the same place. So if I'm going faster than the speed of light, it just means my light will never get to you. You won't know I'm there. But it's loud. Einstein said so. We just don't remember.
Okay, sorry, the website keeps reloading, so I keep losing my place. You talked about how the universe started. How do you think the universe will end?
Well, we have a story. We know that the universe is accelerating now. So why wouldn't it continue to do that? So if it keeps on doing that, then the age it will just keep on doing it an unlimited number of years. So what happens then? Well, the calculation says the stars will all burn out. Then if you wait long enough, what's left is the burnt out remnants will merge together to make black holes. And what happens then? If you believe Stephen Hawking, they will evaporate. And then the universe is extremely empty. Nothing but the tiny particles left over from the decay of black holes. And how long will this take? Unbelievably long. It takes too many zeros to even name the number. But people have worked it out. People think they know. Now, I'm not waiting.
Okay. If the L2 Lagrange point is always shaded by the Earth, how do the solar panels on James Webb work?
We don't stay at the Lagrange point. We orbit around it. We're actually several 100,000 kilometers away from that spot. We definitely do not want to be in the shadow.
Let's see. Are you concerned in any way that we will not be able to explore the X-ray range of space as Congress has lowered the funding for the Chandra X-ray Observatory?
Yes, we're concerned about that. Astronomers generally hate this fact because the Chandra Observatory is the most powerful one we have, and it's actively in use all the time. So I'm kind of hoping that we'll get a new political world that will change that budget. But right now, that's what we have to do. If Congress doesn't send you the money, you have to do something else.
Why use hexagons for the telescope if they do not produce a straight image? Would there be another planar polygon that would produce a better image?
Well, our job is to make the biggest possible mirror, but we have to make it out of smaller pieces. So there are basically three ways you can use regular polygons to do that. They can be triangles, squares, or hexagons, and that's the only three choices nature gives us. So the hexagons are the easiest. They're closest to being round. And so the rounder the better for how you make them.
Let's see. I'm just trying to. So there's a lot of questions that are the same. Do you want to comment on the Hubble tension? You've got this question a couple times.
The Hubble tension. So the Hubble tension refers to different ways we have to calculate the rate of expansion. So if we've understood everything correctly, they should all agree. And they don't. And the harder we work, the more they don't agree. So that means we got more and more precise measurements that can't all be accurate. So what's the difference? What's the problem here? Well, I'm an experimenter, so I build stuff and I'm afraid I made a mistake. So that's my general strategy. I think I made a mistake. Um, but I shouldn't be ignoring the possibility that the universe is more complicated than the rest of us think. And so my gut feeling is we made a mistake, but it would be really exciting if the universe is more interesting.
Yeah.
So we'll find out. But we're huge teams of people are working flat out to try to figure this out, and they don't suddenly somehow agree. They keep finding results that agree with themselves.
Let me see. Yeah. How did winning the Nobel Prize change your life?
As little as possible. I already had a job. I kept on doing the job. It was basically to work on the Webb telescope.
Do you believe in a multiverse? This is getting back to the
Multiverse.
effect.
So the multiverse is a question of, is this universe the only one? And you would have thought, well, there's the only one, because that's plenty enough, long time ago. Then we came up with a story that explains the expansion. And the invention is a possibly imaginary quantum mechanical field called inflation. And you imagine a universe filled with this particular substance, and it compels the universe to expand very rapidly, exponentially. So that explains what we've seen. But it also suggests, well, why couldn't it do it again somewhere else? In which case there would be many, many, many universes, and we would never know about them, probably. So far we haven't seen any sign of another universe, but what would you look for? You'd look for something that doesn't match the current story. So maybe that side of the universe over there is just a little different from that side over there, which says something's funny going on.
What do you think are the biggest questions in physics and astronomy right now?
Well, they're the ones you can answer and the ones you can't. The ones you can't are probably the dark matter and the dark energy. What are they? They're too hard to answer anytime soon, unless we get lucky and somebody finds dark matter in a lab. But we've had like 40 years of working on that in the lab and nothing yet. So that one's a hard one. The understanding of quantum gravity, if there is such a thing, is we don't know how to get at that from experiment. So we're stuck with having to just think. And that's a lot of people are doing it, but we don't feel happy with the answer. So you probably heard about string theory a lot. It was a very promising story. People are not satisfied because it doesn't work well enough yet. So anyway, it was a good idea, by the way. That is intended to address the problem that if a particle is a point, then the energy contained in the fields around it is infinite. So that's annoying. So maybe it's not a point. Maybe it's stretched out into a string, and maybe the vibrations of the string matter. And so lots of concepts that were developed to work on this are pretty fascinating, but we're just not done yet.
Yes.
So then there's all the questions about what happens when you get many things together. There's a famous phrase that says more is different. So if I have 100 molecules and I let them go, that's fairly simple. If I have 100 trillion molecules together, there you are. You're different. Nothing about physics would tell you that you're going to exist. So that's where you go from what physics can do to what you have to just look and see what has happened. You cannot predict biology, you cannot predict culture, you cannot predict information. What you see around us is unpredictable. And so we just got to begin to appreciate that and think about what to do now. Yeah. And there's a big unpredictable thing coming next week, right?
Oh, jeez.
I don't know. Physics doesn't help me on that one.
It does not help. And one last question, maybe the most important question. Are you having a nice day?
Yes. Thank you. It's a wonderful visit. Thank you.
And I apologize if we weren't able to get to your question. I have the whole list here, so we'll try to answer your questions. If we can't get Dr. Mather to answer them, our research group can answer them for you. So we'll try to do our best. We have everyone's email address, so we'll get back to you on that. Again, another round of applause for Dr. Mather. And we'll have you, if you don't mind, have you take a
head
seat
over
over
there.
there. And folks, if you want an autograph, he has a few signed copies of his, a few copies of his book that he's happy to sign and give